In this concept, we're going to talk about symmetry and dilations. So if a figure has symmetry, then it mirrors itself after a transformation is performed. So there are different types of symmetry. We have line symmetry, also known as reflectional symmetry, and that we get if a figure has reflectional symmetry, then one half mirrors the other half, right? So you can see here, for example, for a trapezoid, right, if this is the line of symmetry, then these two portions, or two halves, are mirror images of one another. Okay, this is known as reflectional symmetry. Another type of symmetry is rotational symmetry, where we get the same figure if we rotate the figure that we have less than 360 degrees about its center, right? So rotational symmetry is where you get the same original shape of the figure if you rotate the figure by less than 360 degrees, right? Because if you rotate anything by 360 degrees, you get the same thing, right? But if it has rotational symmetry, then there are other instances or angle values before 360 degrees that will still give you the same original shape. Here's an example of this. So for an equilateral triangle, just like we have here, if we rotate it 120 degrees about the center, right, this, let's say we rotate clockwise, right, so this point ends up here. So this is what we get, right? And the shape, the final shape, is the same as the initial shape. So every 120 degrees of rotation for an equilateral triangle gives us the same starting shape. Okay? Now we want to talk about dilations. Dilations are transformations that change the size but not the shape of the figure. So a dilation is not an isometry since the size of the figure is changed, okay? The size is changed. Remember, for isometric transformations, the size is not changed. In a dilation, a figure is either enlarged or reduced. The image is similar to the pre-image. So there is a similarity, but the size is different. The dimensions of a dilated figure are multiplied by a constant scale factor. So we get the image by multiplying the pre-image by a constant scale factor. Let's look at an example of dilations. Here we have this square of sides 2, side lengths 2 units each. And we basically dilated by a factor of 2, right? And what that gives us is, pretty much, it's very straightforward, right? So every side is multiplied by 2, so then we end up with this new square, right? With each side having length of 4 units. Okay? So we say that this square has been dilated by a scale factor of 2, so it has basically been enlarged. So when enlarging a figure through a dilation, the scale factor is greater than 1, right? Has to be greater than 1. When a dilation reduces a figure, the scale factor has to be between 0 and 1, which makes sense, right? So it's either a fraction, fraction or decimal, but it's basically between 0 and 1. And that means that the original shape would have gotten reduced to a smaller shape. Let's look at further examples of dilation. Classify each dilation as either an enlargement or reduction. Then determine the scale factor. So we have this triangle. One side is 4, the other side is 2. And then we have this triangle. One side is 6, the other is 3. So we can take the ratio of any of the two similar sides, right? So here we have, but you take the image, divide the length of the side from the image divided by the length of the similar side from the pre-image, right, to determine the scale factor. So we take the 6 units of length here and divide it by 4. Or we could take the 3 from here and divide by 2, and both of these give us the same thing. So the scale factor is 1.5, so that means the figure has been enlarged in this dilation. Let's look at this example. So we have this rectangle, this side is 10, this side is 5, and then it becomes this rectangle, one side is 4, one side is 2. Right? So remember, we take the length from the image divided by the length of the similar side from the pre-image, so 4 divided by 10, or we could take 2 over 5, right, 2 over 5, and they both give us the same thing, 0.4. So the scale factor is 0.4, therefore this figure has been reduced, because the scale factor is a decimal between 0 and 1. Okay? And here we have some exercises. Please pause the video, work on these, and come back for the solutions. Okay, so determine whether the following figures have reflectional, rotational, or no symmetry. For an isosceles triangle, so two sides equal, right? So two sides equal. It doesn't have rotational symmetry because there's no way to get back to the same shape unless you actually rotate by 360 degrees, right? Like if you rotate by 90, it doesn't work, by 180 doesn't work, 270 doesn't, no angle gives you the same shape like an equilateral triangle. No angle gives you the same shape other than 360 degrees, so it does not have rotational symmetry. It does have reflectional symmetry though, and it's very clear, right? So if you drop a line like this, right, center, so these two triangles will be congruent. So it does have reflectional symmetry. Okay, so isosceles triangle has reflectional symmetry. For a square, well, square's got a lot of symmetries, right? So it does have rotational symmetry because you can rotate by 90 degrees and still end up with the same shape, right? Or 180 or 270, right? Or 360 obviously is not one of them, but you can rotate by multiple angle values under 360 and still end up with the same original shape. So it does have rotational symmetry, right? And if you cut it whichever way, so you can cut it this way, then yeah, it does have reflectional symmetry about this line. Or if you cut it this way, it does have reflectional symmetry, so it definitely has reflectional symmetry as well. Okay? For a scalene triangle, so remember, a scalene triangle is a triangle that has 3 unequal side lengths. It doesn't have rotational symmetry because, again, there's no angle value that will give you the same shape as the original shape other than 360 degrees, where, it goes back to where it started from. So that doesn't count. So it has no rotational symmetry, and it does not have reflectional symmetry either, because there's no way to cut it to get two congruent triangles, right? If you cut it this way, the triangles are different. If you cut it this way, these are not the same. If you cut it this way, for example, right, they're not the same. There's no symmetry. There's no reflectional symmetry. So a scalene triangle has no symmetry. Okay? And this is it for this concept. See you in the next video.